The Recyclyze project set out to develop new electrocatalysts for PEM electrolyzer systems, with increased performance, reduced critical raw material usage, reduced environmental footprint, and reduced total costs. Then another important goal was to develop processes for recycling of the critical raw materials to decrease the dependence on materials imports. Reaching ambitious goals like these is always challenging. Furthermore, the project kicked off during the first COVID-19 lockdown, which meant that many of the partners' labs were closed and travel and visits were prohibited. However, a strong consortium showing great commitment has resulted in a focused effort all throughout the project, as well as excellent collaboration. So this strong collaboration has been paramount in order to achieve the ambitious goals and objectives of the project, as the work from the various partners is strongly tied together.
In Recyclyze, University of Bern started by developing a standardized protocol to test the performance of anode catalysts in rotating disc electrodes and gas diffusion electrode setups. Afterwards, we focused on the synthesis of highly active catalysts. We were able to synthesize a colloidal iridium and iridium rutheniol nanoparticles via straightforward oil bath synthesis and then immobilize them on the different supports. The supports were first commercially available ones, and later the ones synthesized in the project. Out of the synthesized support materials, the most promising one in terms of electrical conductivity and large surface area is antimony doped tin oxide. Fraunhofer Institute for Chemical Technology optimized the Solger synthesis and were able to achieve electrical conductivity values that are a factor of 10 times more higher than the ones of the commercially available ATO from Alpha Esa, and BT surface areas which were a factor of 50% higher. Afterwards, we successfully scaled up the synthesis, which was necessary for the combined upscaled catalyst fabrication. Another focus in Recyclyze was to reduce partially or completely the amount of critical raw materials in the catalyst. This was achieved by mixing gold wires with manganese oxide particles. This bimodal system has shown promising first results and will be implemented in the membrane electrode assembly single cell.
The fabrication process is aimed at upscaling the catalyst synthesis, fabricating and testing produced electrolysis cells. The catalyst upscaling was performed by DTI at 2 separate stages, following the material development effort split to 1 CRM-rich and 2 CRM-reduced catalysts. DTI managed to increase the activity of the catalyst by a factor of 20 on electrode level compared to the state-of-the-art commercially available catalysts. Also, production rates of up to 50 grams of catalysts were achieved at a reduced fabrication costs and material waste by utilizing a flow production method. The upscaled catalysts were delivered to Blue World Technologies, where electrode and cell fabrication took place. We developed several production methods based on decal and spraying techniques. 2 cell sizes were pursued, 4 and 75 square centimeters active area cells, for development and stack testing respectively. The strong feedback loop between material production and testing at Fraunhofer ensured an efficient system optimization. Electrode production by robot spraying was optimized to reach a capacity of above 1 square meter per hour. Fine-tuning the cell configuration resulted in high activity and prolonged durability, even at low iridium loading of 1 milligram per square centimeter. The second generation of the CRM-reduced catalysts demonstrated a cell performance of more than 4.5 amps per square centimeter under 2.5 volts. The electrolysis stack was assembled with the optimized cells, totaling in 1,000 square centimeters of active area. The stack was then sent to HiCenter for testing.
The demonstration of functionality and scalability of the developed catalyst and support materials is an important milestone within the Recyclyze project. In order to show the successful operation of the stack with the lower catalyst loading, at the HiCenter we built a fully equipped electrolysis stack testbed. The testbed can carry out all kinds of state-of-the-art electrolysis tests to identify limiting factors within the catalyst development. This helped for further improvements within the production process and remove weaknesses. Furthermore, the testbed is capable of online gas quality measurements and identifying impurities within the produced hydrogen. With this setup, harmful as well as insufficient operation states were identified, and together with all results gathered, the operation strategy was optimized. The optimization of the operation strategies was carried out by Prüfrex with a simulation-based approach. which included the development of a simulation model of the electrolysis system to reduce cost-intensive evaluation at the testbed. The model was subsequently used for optimizations of the layout, the control strategies for longer lifetime of the stack, and a sensor virtualization approach for lower system costs. During the project, 2 stack generations were developed and tested at our testbed at HiCenter. While the first generation stack showed challenges that needed to be addressed, the second generation stack performed well with low catalyst loading.
Within Recyclyze, the recycling strategy was proposed for the novel composition of electrocatalyst to enable the circular economy of critical raw materials. First, the de-assembly concept for PEMEC was developed at Acorec to separate the membrane electrode assembly from the stack and to recycle bipolar plates. The MEA was then undergoing 2 approaches. The one, so-called cathodic corrosion, investigating the possibility of reactivation of the spent MEA at TWA, and the second one was a conventional recycling approach, where the valuable metals were extracted through the hydro- and pyrometallurgical routes. Here, TU Freiburg developed the environmentally friendly and economically attractive recycling process to achieve above 90% recyclability of the spent electrocatalyst, and patented a novel approach for ruthenium recovery. The further focus was on the recovery of valuable metals in the form of precursors that can be reused for electrocatalyst fabrication.
The Recyclyze project has within the last 3.5 years developed innovative, recyclable electrocatalytic nanomaterials made up of bonded elements in order to disrupt the energy storage market. The project has developed new materials with a significant reduction in the use of fragile raw materials in PET electrolysis. Furthermore, we have developed recycling processes for the materials used in PET electrolysis and shown that such processes are beneficial both economically and environmentally. The ambition of Recyclyze was to overcome the main existing barriers for PET electrolysis to penetrate the market, namely the price, accessibility, and performance of electrocatalytic materials. And the new materials and processes developed in the project will indeed contribute to this.